Hello and welcome to your Lecture 9 skill check. Here today we're going to talk about linear regression. So here is the scenario, and I want to emphasize that in this case we're actually using real life data, although the scenario itself is made up. So here we imagine that the chief medical director at New Amsterdam Public Hospital, Dr. Max Goodwin, wanted to see whether there is a relationship between a person's percentage body fat and their age. So he collected data. X would be the age, that's the predictor or independent variable, and Y is the percent body fat, that's the response or dependent variable. Data was collected from 250 randomly selected adult patients. And we're kind of pretending that you've been hired to conduct the analysis of the data. And so hopefully you've done that already. And here we can see how well you did with that analysis. So the first question was to look at the scatter plot and to explain why it is appropriate to fit the linear model to this data. And the basic idea is the data cloud, if you will, should look as if there is a linear relationship. And so here, I think we can easily imagine a straight line passing through this data. It does look as if there is a slight upward slope and a linear trend in this data. And so, again, before fitting a linear model, you should ask whether it looks like there is a linear relationship between predictor and response. Here, the answer is yes, so let's regress. The second question was to use information given by Minitab to write the equation of the linear model and then to provide an interpretation of the model coefficients. So the general form of the model is we have an estimate of the population mean response at a given value for X. And that estimate is based on these two model coefficients, an intercept and a slope. Now I want to just draw a clear, bright line between, on the one side, what we call population parameters. The population parameters in simple linear regression include a population intercept, that's beta 0, and the population slope, beta 1. The model coefficients are the B0 and the B1 that you get when you do the analysis. So let's just make it clear. We have population parameters on the one hand. These are the things we don't know and that we are trying to estimate. We have model coefficients on the other side. These provide point estimates of those population parameters. So in this case, we can read those point estimates from the table. We have an intercept of 10.53% and a slope of 0.1934%. So let's look at this interpretation. So here we have our axes. We're going to label them. The x-axis shows the age, the y-axis the percent body fat. Now, the intercept shows us or tells us where the modeled equation crosses the vertical axis, the y-axis. So in other words, if you take this model equation and you put 0 in for x, what you will get out of it is just that 10.53%. So that is the intercept. The slope tells us that for every extra year of age, on average, we expect to see an increase in the percent body fat of 0.1934%, about 19%. Right, so the model predicts an average increase of about 0.19% body fat for every additional year of age. The intercept, in this case, should not be interpreted. And that's because x equals 0 is beyond the range of the data used to fit the model. So this has something to do with what we call extrapolation. Extrapolation is a word you would have learned in 2208. I'll say more about that in just a moment. But first, I just want to emphasize It would be tempting to say that when x equals 0, that would represent a newborn baby. It would be tempting to say that the model is predicting that newborn babies on average have a percentage body fat of about 10.53. The reason that's not correct is because when we fit the model to data, our data included only ages between about 22 and up to 81. In fact, the smallest age in our data set was 22 years of age, and the largest was 81. And so what that means is we can say nothing about this association between age and percent body fat for ages less than 22 or more than 81. And that's because going less than 22 or greater than 81, that's extrapolation. That would be extrapolating. And that would basically be assuming that this linear relationship exists beyond the range of values for which we can actually see the data. Right, so the model cannot be used to estimate population mean response for any person less than 22 or more than 81. And again, mainly because we don't have data for individuals less than 22 or more than 81. And so we have no way to know if the linear association that is evident in the data that we do have, we have no way to know if that linear association extends beyond the range that we can see. So that to do so would be called extrapolating, and extrapolating in this context is something you're not supposed to do. Question 3. Looking at the scatter plot with the line of best fit, can you see any data points that look unusual in any way? And essentially we're talking about data points that have unusually large residuals or that are leverage points, meaning that they are far away from the rest of the data in the x direction. And so with this plot, I think most people might look at this data point and say, well, this one has the largest residual and it looks a little bit unusually large compared to the rest of the data points. So this we can identify as an unusual data point. A potential problem, we may or may not want to remove that data point. Some of you might also have identified this data point as a leverage point. And why? It's because this data point is a bit further in the x direction. It's a bit far in the x direction from compared to the rest of the data. Right, so here there are two data points that look a bit unusual. There's one with a large residual and one leverage point that is potentially influential. Now I'm going to pause for a moment here and go to Minitab, and I want to say a little bit more about these unusual data points. So this is the analysis in Minitab. You can see up here we have our line of best fit. On the side we have some information regarding the R squared. We have the R squared. Now, if you bear with me for a minute, I should have done this already, but I'm just going to make the font a little bit bigger so it's easier for us to see. Okay, that's better. And so here's what we can do. We can find this data point and remove it from the analysis and then see how removing it changes the slope and the coefficient of determination. We'll do the same for both of these points. So I think actually I'm going to start with this data point. This is a leverage point and it's potentially influential, meaning that if we remove it, the slope might change by a lot. So how do we remove this? Well, we have to find it. We can see here this data point is in row 77. So I will go down to row 77 or up to it. There it is. So row 77, you can see that the age is 81. There's the age in the second column, the percent body fat in the first column. So we can simply delete those cells. Now that data point is removed, and we can update our results. And so what do you notice? The slope now Well, it's still about 19.19%. Previously, it was 0.1934. Now it's 0.1977. So it didn't change by very much. We can also have a quick look at the R squared. Just make that bigger so we can see it. And here you can see the coefficient of determination. It was 8.7. Now it's 8.8. So it hardly changed at all. So what we're saying is this leverage point is not influential, because when we remove it or when we include it, in those two cases, there's really no difference in the estimate of our slope. Also, there's no difference in the R squared. So it's not influential. So we can put that point back in. We just go up here. We undo that removal. Now that data point is back. Whoops. Oh boy, this is frustrating. Let's see. There we go. So we'll update the results. Now you can see that data point is now back in our data set. Let's just do the same with this data point. This is the one with the large residual. And that, just pause for a second, think for a moment. What will happen to the coefficient of determination, do you think, if we remove this data point? So you should be telling yourself that if this data point with the largest residual is removed, the coefficient of determination will get a little bit bigger. That's because we're removing some of the randomness from the data. And so that makes the systematic component of the data, that makes it a greater proportion of the total variation. Well, you don't have to take my word for it. Let's see what happens when we remove it. This data point is in row 214. So I will just go down there and we'll knock it out. 214. So we'll take this row. We can, delete it. Delete cells. Now it's gone. And all we have to do is update results and see what difference it made. So remember, with that data point, R squared was 8.7. The slope was 0.1934. When we remove it, the slope gets a little bit smaller, but it's still about 0.19. And the R squared stays more or less the same. Right, so that data point is also not problematic because it makes no difference whether we include it or not. And so we might as well include it. So how do I do that again? Oh yeah, I go up here. I do that, update the results. And we see that, yeah, that data point has come back. Okay, so I think we can close this now. There's nothing else I want to do. With Minitab, returning to the slides. So once again, these points you could identify as potentially problematic. They are unusual. One, it's unusual because it's far away in the vertical direction, and the other is because it's far away in the horizontal direction. But by removing those data points and comparing the analysis with and without, we can see they really make no difference, so we might as well include them. If this leverage point, for example, makes a big difference in the slope, then we would consider removing it from the analysis. Right, so this slide just reviews the concepts, the large residuals. These are observations that are far away from the line of best fit, meaning that they have an unusually large residual error. And leverage points are observations that are far from the bulk of the data in the x direction. And leverage points are potentially influential. We saw here a case where we have a leverage point that was not influential. Sometimes they are, sometimes they're not. Question 4. What are the 4 conditions required for simple linear regression? Well, these you should know by heart. You should have these memorized by now. We need to know that the association between the predictor and response looks linear. So that's the linear enough assumption. We need to see a constant spread in the variation in the vertical direction. We need to see that there's no unusual data points, which we just checked. And we also must confirm that the residual errors are approximately normal in distribution. So all of these things can be checked simply by looking at the residuals. So here we look at the normal probability plot of the standardized residuals and also the versus fit plot. So one thing to check we can see immediately is if the residuals follow a normal distribution, then most of them should be within 2 standard deviations of the mean. And you can see from all of these plots, you can see that's the case. Here's 2 standard deviations below and above the mean, and most of those data points are within that range. Here too, you can see it. In the histogram, you can see it. And in the versus order plot, you can see it. So that's one thing just to check. The next thing, though, let's consider the linear enough association. We should see that the data cloud in the versus fit plot looks flat. In other words, there's no upward or downward trend in that data cloud. And this is certainly the case here. So we are linear enough for sure. Next, we can check out the vertical spread. So we can see here the spread in the vertical direction is pretty much the same as we move across the horizontal axis. And so the constant spread condition looks like it's satisfied as well. In terms of unusual data points, we've already identified this one data point which has a residual that's a bit larger than the rest. And we also have this other data point that is a bit of a leverage point. However, we've already determined that these 2 data points don't pose any problem in our analysis, so we have no reason to worry about those. So we're good with those. And lastly, we need to check the normality of the residuals. So here, all you're checking is that in the normal probability plot, these data points representing residuals, these are in an approximate straight line. If the red line is included in the normal probability plot, it isn't always included, but here it is. If that red line is included, then these points should be in a straight line on top of that red line. So here we can see that that's pretty much the case. So approximate normality is apparently satisfied. Now you might have noticed that in the histogram, the histogram appears to be bimodal. And if the data set was small, let's say we only had 30 or 40 data points, 50 maybe, in a small data set, bimodality in this histogram could just be a result of sampling variability. However, with a big data set like this one, 250 data points, I would say that this bimodality is something that's really in the data. There really is some kind of bimodal distribution in the data. Now, you might be able to guess what that is. I would guess that there's a difference between the relationship between age and percent body fat. There's a difference between adult males versus adult females. So it could well be that this bimodality is a real signal because of that difference. In any case, we still have approximate normality. So this bimodal indication, this hint at a bimodal distribution, in this case, it's just very subtle. It's not really enough to make a difference. So we can go ahead and conclude that the residuals are approximately normal in distribution. We can be happy with that, which means we can go on to do our inferences. So turning to inference, here we're going to use the information from the analysis of variance table. Here we're just computing the coefficient of determination. The point of this exercise is to help to sort of get it into your head what sums of squares measures and what the coefficient of determination measures. And so just to go through that again, a sum of squares is a measure of variation. And so the fitted values have some variation as measured by this quantity. The data itself, the y values, have some amount of variation. And r squared is simply the proportion of the total variation in your observations in the y values that is taken up by the fitted values. So in this case, as we saw earlier from the Minitab output, it's about 8.71%. From this, we can easily calculate the correlation coefficient. It's just the square root of r squared. Don't forget, when you take the square root, that r squared should be in decimal form, not percentage form, if that makes sense. And so here we can see our correlation coefficient is pretty low, and that makes sense because there's a lot of scatter in the data. Now, what do these things actually mean? The coefficient of determination tells us that about 8.71% of the variation in percent body fat in our sample can be attributed to differences in age. And what that means is more than 90% of the variation in percent body fat is left unexplained by the regression model. Now, I would say that some of that unexplained variation could be explained if we included in our model a way to differentiate between, say, adult males versus adult females. Right? So I'm referring to that bimodal distribution that we saw earlier. So there are ways to include other predictor variables in a regression model, more than just one. Here we only have one, it's age. There's ways to include more, and we're going to learn about that later in the course. So what I'm saying is some of the variation that's being left unexplained by differences in age could be explained by differences in between male and female. Probably most of that variation, however, most of this unexplained variation is due to individual differences. So differences in people's health status, in their diet, in how much sleep they get, how much exercise they get, what kind of job they have. All of those differences, not to mention just genetic differences, all of those differences, all of those individual differences would contribute to most of the unexplained variation in this scenario. Just to rehearse what the correlation coefficient means, remember that this coefficient provides a measure of the strength of the linear association between your two variables, in this case, percent body fat and age. In this case, that value is low, and so that indicates a relatively weak linear association between this predictor age and the response variable percent body fat. Okay, so let's use the information again. This is a Minitab output. We can use this information to construct a 95% confidence interval for the population mean slope. Right, so let's go for that. Well, we need to remember that the sample size is 250. And why do we need to know that? Because we're going to need to determine a critical value for our confidence interval using a t-table. So the degrees of freedom in a regression analysis, in this simple regression analysis, is 2 less than the sample size. So in this case, 248. So if we go to a t-table, we can see the t-table has 250. We can't use that because it's too big. 180 we can use, and so for a 95% confidence interval, the critical value is 1.973. So returning to the slides, we're going to construct a confidence interval. So that's the point estimate plus or minus a margin of error. The margin of error is the product between our critical value, which we get from a t-table, and the standard error of our point estimate. And so here we just take values from the table. So you can see that the point estimate is 0.1934%. The standard error of that model coefficient, 0.0398. And then here we have our critical value from the table. And so we can then calculate the lower and upper bounds for our interval. So what does this interval mean? Well, we can say that we are 95% confident that the population parameter, beta 1, which represents the average change in percent body fat for each additional year of age, is between 0.11% and 0.27%. Furthermore, because the lower bound is greater than 0, this lower bound, we can infer that beta 1 itself is not 0, and therefore that the percentage body fat tends to increase with age. In other words, there is an association between age and percent body fat. Question 7. The second kind of inference is to do a hypothesis test. Here, we're going to test the hypothesis that the population slope is 0 versus that it is not 0. And we're going to test at the 1% level of significance. So before we do anything else, we need to look up a critical value for 1%. So this is a two-tailed test. We want to put 0.5% into each of the tails. And so easily enough, we can look at our t-table. Two-tail probability should be 1% in total. In other words, 0.5% in each tail. We go back down to 140 and we get a critical value of 2.611. Yeah, okay. So going back to the slides, I see that I made a slight error here. So let me just quickly correct that. Okay, so now let's look at the animation. So again, sample size 250, it tells us the degrees of freedom is 248. We're going to calculate our test statistic. It's just equal to the estimate of the population slope compared with what is hypothesized under the null divided by the standard error of that point estimate. So we're just taking values from the table. It's very easy to do the calculation. You can see that our test statistic is quite large. And we can compare that to our critical values. So here again, this was the critical value that puts 0.5% into each tail of the distribution. 99% in the middle. This again is the distribution of our test statistic, assuming the null hypothesis is true. If the null is true, then a test statistic as big as this one is highly unlikely, and therefore we have evidence that the null is not true. So our test statistic is larger than the upper bound of our rejection region. The test statistic is greater than the rightmost critical value. We can therefore conclude at the 1% level of significance that the population parameter beta 1 is not 0, and that the quantitative variables y is percent body fat, x, age, that these are associated, right? If you do not reject the null hypothesis and cannot conclude that the true population slope beta 1 is different than 0, then you cannot say there's an association between your predictor and response. It's only if you reject the null that you can say there is an association. There's evidence of an association. Okay, so the last question I asked was sort of a challenge question, and that is, could the population slope be different than 0.25% body fat per year of age? And we're going to test here at the 5% level of significance. So this is really not that much different than what we just did. All we need to remember is that our hypotheses are changed. The null hypothesis is that the true slope, the population slope, is 0.25. The alternative is that, that it is not equal to 0.25. So here's another little typo. No worries. Okay, let's go back. Right, so it's a two-tailed test, but instead of putting 0 here, we're putting another value. So how does that change the calculation? All it means is instead of putting 0 here for the hypothesized value, we put in 0.25. Apart from that, everything else is the same. So here we get our test statistic. We need to compare that with our critical values. So if we look at the t-table, you'll see that the critical value for a 95%, for a 5% test, two-tailed test, it's the same as the critical values for a 95% confidence interval, which we looked up earlier. These are the values that put 2.5% into each tail, which means 95% in the middle. And clearly, this test statistic is inside this interval, and so we have no reason to reject the null hypothesis. So in the end, we do not reject the null hypothesis and can therefore conclude at the 5% level of significance that there's no evidence that the population parameter beta 1 is not 0.25. And in fact, this is consistent with our 95% confidence interval for beta 1, which we found contains 0.25. This was the confidence interval we found earlier, And you can see 0.25 is inside this interval. It is therefore a plausible value for the population slope. Okay, so that is the end of this. I hope you found that useful. Remember that if you have any questions, anything was unclear, just jot down a question in the comments. I can reply in the comments, or if you prefer, you can ask me in class. Great. Okay, so that's it. Thanks for watching, and see you next time.